some set of ideas. Let's go back all the way. So the idea is try to understand asymptotic normality results similar to what we have for the sample mean. So you have an estimator, let's say in this case the sample mean, which is a consistent estimator of the mean, and then you'd like to prove a perturbation sort of bound, or understand like how close you are to the true parameter, or the estimators to the true parameter. And classically, the central limit theorem gives you such characterization. If you properly normalize the deviations of the estimator from the true parameter, then these deviations converge in distribution to a multivariate normal, and then you can use that information to build confidence intervals or confidence sets or U hypothesis testing, or basically anything you want from a statistical perspective. So we want to extend this result to general, let's say, M estimators. In order to do that, we sort of developed some calculus rules to deal with probabilities and, the convergence in probability and convergence distribution. In particular, continuous mapping theorem. So if you apply any continuous function to a sequence that's converging in probability or in distribution, then you would get that the results for the f applied to that sequence. And then there's the Slotsky's theorem that says that if one sequence converges in distribution to some random variable, the other one converges in distribution to some constant, then the pair converges in distribution to the limit. And so the consequence of combining that idea with the continuous mapping theorem would lead to these ideas that we have here. And so you can use this to drive a lot of interesting results. One in particular is that little OP01 plus little OP01 is equal to little OP01. Little OP01 means sequence converging to zero probability, or you can interpret this as in distribution. We went through counterexamples and example. Then we introduced this idea of uniform tightness, which corresponds to bounded sequences in probability uniformly. So uniform means over the sequence at n goes to infinity, there's like a fixed interval that we can contain all the distributions within that interval with a certain level of confidence, epsilon, let's say. And then the idea is that uniform tightness implies, convergent distribution implies uniform tightness, but not vice versa in general. And that if a sequence converges in probability to zero, and another sequence is uniformly tight, then the product is converging to zero. So this tightness is written as big OP01. And so we can compactly represent the first statement as little OP01. And big OP01 is equal to little OP01. Yes.
So this time, can you do like arithmetic with like the little OP and big OPs? Like, can you distribute over sums of the little OP and big OPs?
Every step you have to justify, basically. Yeah. So justification comes from these results. So it's not like usual arithmetic. So you can say little OP01 plus little OP01 is two little OP01, but two little OP01 is just OP01. But this statement requires justification, and justification comes from here. So if you have like little OP01 times the other side, can I conclude? So for example, you have little OP01 times this thing. Can I distribute, say, basically, I mean, the end result is like, is it going to be equal to little OP01? Is that true or not?
Yeah.
So why is that? The question is like, can we do so if I multiply both sides by OP01, is this going to be true? Otherwise, like, can we justify that? So you don't need to say it's going to be OP01 times OP01 because it's going to be still.
It's just continuous mapping, right?
Continuous mapping.
Like the product of the two sequences of variables.
Right. Okay. So that's an instance of this result. Yeah. So you can say this is like that, or just what we talked about. This is going to be big OPL1 as well. So this is like even better. So OPL1 is better than OPL1.
Yeah.
So little OPL1 is definitely big OPL1 as well. So you can write something like, if you write this as OPL1, this is fine because sequence of conversion is 0. Like this is not necessarily, so you shouldn't have to like interpret this the other way. So this maybe I should remove it. It's like, but a sequence which is little OPL1 is definitely big OPL1. So, but you can also use that this is little OPL1, this little OPL1 product is little OPL1 into this result as well. So multiple ways of doing it. So if you're careful and can justify each step, then you could do calculus. That's basically, yeah. Okay, other questions? And there was this idea of uniform, stochastic equicontinuity, which is another notion of uniform sort of convergence or uniform continuity, which applies to a class of functions. So I'm not going to go into the details of, again, what this is. The main point is this consequence. We're saying that if a sequence is stochastically equicontinuous at a point, and I have another random sequence that converges in probability to some fixed theta naught, then I can basically, when I look at the sequence of functions evaluate at theta hat n minus fn and evaluate at theta naught, this converges in probability to 0. So basically what this is saying that is I can write something like that. Fn theta hat n is going to be equal to Fn theta naught plus little OPL1. Okay, I can do this procedure. I can replace this with theta naught and then pay a price, which is a little OPL1. So if you, again, recall what this notation means, this green statement is exactly the same as the conclusion of that here. Okay. So this allows you to like simplify expressions by, so this is going to be in general very tricky to deal with. So this is something the proposition does not assume anything about the dependent structure of Fn and theta hat n. So they could be very dependent, but this allows you to replace that conveniently the argument with a constant, and this could be much easier to deal with later. Okay, that's the main purpose of introducing that condition. So questions? Okay, so that was a recap. So let's go back to the setting that we were. You started talking about M estimators in that setting. So the setting is that we have like an IID sequence from a true model, and then we form this M estimator, which is obtained by maximizing this function Mn, which itself is an empirical average of these little M thetas applied to each one of the observations. Okay, so this Mn is a random function, right? But has a particular structure, which is like an empirical average of a bunch of IID terms. Theta naught is a true parameter, and let's introduce these notations, which is similar to what we had for score function. So the a single dot on top of M means derivative with respect to theta. Okay, and then a double dot means second derivative with respect to theta. And if you really want, this is really Hessian. I'm writing it like that for simplicity, but this is a matrix if theta is in RD. The first one is really the gradient. So if theta is in RD, this is going to be in RD, this is going to be a D by D matrix. Okay, so that's the Hessian of that function evaluate theta naught. First one is the gradient. And similarly, we'll put a double dot on top of capital Mn to mean the second derivative of Mn, and so on. Okay, so these are the notations. So setting is clear. Okay, so now the statement is something like that. So Oh, okay. And then to simplify, I sometimes drop the dependence on xi. So these are random quantities. To simplify the notation, I just drop this. For example, because they're IID, then I take the expectation. So something like expectation of this, when I write something like I mean expectation of this guy. This could be like xi for any I. It doesn't matter because they have the same distribution. They can treat it as just x1. So that's the meaning of these expressions. And so with these, you have this result. So if theta naught is in the interior of the parameter space, which is a subspace of Euclidean space, d-dimensional Euclidean space, and we have these conditions. So the first one saying that the expectation of the derivative of the gradient of m at theta naught is 0. So let's have in mind, for example, a very typical case, which is this is log p theta of xi. So m basically, m theta could be the log likelihood. And so this m dot in that case, so if m theta is like this, then m dot theta naught of xi, what would this be called? Score function, yeah. So this is the score function. And we have seen that under the regularity assumptions, the score function, the ones that we had for the Cramer-Rao bound, score function has 0 mean. So this makes sense. So this you'd expect to hold for other reasonable M estimators. And then I have the this quantity, which is now going to be the covariance matrix of m dot, because m dot theta naught is 0 mean. So this is really the covariance matrix, if you remember. So I'm calling it as theta naught, and we're assuming these are well defined. So they exist basically. So the second moment that this exists, and if they are well defined, this quantity is integrable. And I'm going to call this S theta naught. So for example, for the likelihood case or the log likelihood case, what would this guy be? If m theta is the log likelihood.
For sure.
Very close. Like with a bit of a, so you have to flip the sign. So this would be, oh, actually, no, actually, you're right. So this is exactly right. You're right. So this is going to be Fisher information. The other thing is going to be, so the second thing that I'm looking at is the expectation of the double dot. And this would be the negative Fisher information. Okay. Right. So that the first one is the way you define Fisher information. That's going to be the Fisher information. It's positive semi-definite because the covariance matrix. The second condition is assuming that the second derivative is integrable. And I'm going to call this V theta naught. And so in the case of the likelihood, log likelihood, these are very related. So one is the negative of the other, but in general, they could be different. But we're going to assume that this is strictly positive. Sorry, strictly negative definite. So in the case again of the likelihood, log likelihood, so a special case, this would be negative I theta naught, right? The Fisher information. So Fisher information is positive semi-definite. So this is going to be positive definite. We're strictly assuming that it's doesn't have any zero eigenvalues, so it's invertible. And that's part of the assumptions. Roughly speaking, you want to have a maximum. That's the condition. The third is the theta, and it's consistent for theta naught. So you have to establish consistency of the M estimator by other means. So you had a result that does that. So you assume that. And then the last one is that the sequence of second derivative of this is stochastically equicontinuous at theta naught. So this is the main technical condition that allows us to simplify like a critical term in the proof. So on the face of it, the conditions are like fairly benign, except for perhaps D, which is we assume that you can establish by other means. But that's it. Okay, so these are the conditions. Questions? So what is the result? The result is an expansion, like an asymptotic expansion of this deviation. So theta hat n is the M estimator. So this guy, right? The solution of this optimization problem. Theta naught is the truth. And so this is deviation from the truth. We know that this is going to 0 by assumption C. So if I rescale it by root n, the result is saying that the first for the first order term, we have this expression, and then there's this little OP of 1, which is basically saying this is a term that goes to 0 probably. So what is the first term? The first term is V theta naught inverse. That's a like a deterministic matrix. That's this guy times this, which is sort of like a weighted, not weighted, but if you think of the root n, if you multiply it by root n, then, or sorry, divide by root n basically would be like the average. The average of those sort of things that look like a score function. Okay. So the significance of this result is that this part, this is a solution. This is not a sample mean. Okay, so theta hat n is a complicated estimator. However, we wrote the deviation as like a matrix times something which looks like a mean. Okay, and we understand the means very well. Okay, so this quantity is a lot of things going on for it. So CLT, for example, applies to it, right? So we expressed the deviation of this general n estimator in terms of a quantity that we understand. Moreover, that quantity is going to converge to a normal with mean 0 and covariance as theta naught. This part is sort of, this should be sort of clear. So why is that clear if delta n is defined like that?
CLT.
That's the CLT. Yeah. So basically, this is the first condition is saying this is a 0 mean random variable. So fix theta naught. So this guy evaluate theta naught would be basically. So let me do a calculation.
Delta is a function of theta as well. So
yeah. So what we're thinking of the like expansion of theta naught, right? Yeah. So it's a particular point. So this guy would be 1 over. So I'm gonna do this root n 1 over n summation I from 1 to n m dot theta naught xi, right? So this is like an empirical average or sample mean, let's say. Yeah, let's say empirical average or sample mean. And we know that the expectation of m dot theta naught xi is 0, and then the covariance basically is by definition that S theta naught, right? So by CLT, this converges in distribution to, so we have root n times the sample average. So this should converge to normal, which means 0 and covariance this, okay? So that's the advantage of writing that deviation in terms of a, like a scaled average, because then we can use the CLT. Yes.
So is delta n is theta naught? Because when you define it up there, you don't have the 1 over n.
No, yeah, so I have 1 over root n. So I'm like multiplying and adding by, right? Sorry, multiplying and dividing by this. So now this is really the form, if you remember. So you write CLTs like this times, let's say, x bar n minus mu, right? So mu here is 0. So this conversion distribution to normal, which means 0 and covariance sigma. So that's the way that we. probabilists usually write things in terms of the sum, so it would be like 1 over root n summation. Statisticians usually write in terms of the average, so you get a root n on the average. So they're equivalent. Whichever form you're comfortable with, you can write it. Sounds good. So if I manage to prove this, then this part is fine. In particular, there's a second conclusion, which is saying that this deviation is converging in distribution to this quantity. And this is sort of also easy once you have that expansion. So why this one is true? Assume that we know this, we have shown that. So why the second conclusion or the third conclusion?
Just apply the SD over the conversion in distribution, and you multiply by a constant that you get easily say that it's still converging in a distribution and not a random variable, but the variance transformed by the constant.
Good. Yeah, that's exactly it. So you have, for example, let's say I have root n theta at n minus. Theta naught is negative v theta naught delta n theta naught inverse plus OP of 1. Okay, and I know that this quantity the other one inverse. This quantity n theta naught is converging in distribution to normal 0. Sigma, so let's call this, for example, like a random variable z, where z is normal 0. That's sigma s theta naught. So now I can conclude that this guy converges in distribution to negative v theta naught times z. And you can argue it by negative, but by multiple arguments, either like continuous mapping theorem or Slutsky's theorem. Right? The sequence converges in distribution. This one converges in distribution to constant. So you get the product, or you can say this is a continuous mapping. So I'm applying basically a continuous map, which is just this guy, basically a linear map.
With Slutsky, you say it converges to a constant because it doesn't do it converging at all. Like it's a constant in there. It's deterministic.
Yeah, so it does converge to constant, but just trivially.
Yeah.
Right. Yeah. So either Slutsky or like continuous mapping theorem. So this holds, and this is so what is the distribution of this guy? So if z, we know that z has this distribution.
0 mean and then transpose and omnibus.
Right. So we can say that. Yeah. So this is a linear function of a multivariate Gaussian. So it should be Gaussian. The mean would be that matrix times the mean of z, which is 0, and the covariance is, as you guys pointed out, you can figure out what the covariance is. Like you get this times the transpose of it. So this and then transpose here, and then s theta naught, but the transpose is the same as itself. So v theta naught inverse is symmetric, and so you can drop the transpose. Drop transpose. So you get basically, you can say negative here, negative there, and negatives cancel out. Right, so you get this result. So this is the kind of thing that we were after. So we managed to prove an asymptotic distribution, an asymptotic result for asymptotic normality result for the M estimator, and we figured out the asymptotic covariance structure. Okay, so now you can use this to build your confidence intervals or whatever you want to do. That the main part is like proving this and then figuring out what the asymptotic variance is, or asymptotic covariance is. Okay. Sounds good. Yeah.
So what about this step going from like the consistency formula to the V delta and theta?
Yes. We haven't done that yet.
Oh, great.
Yes. So that's the main part, basically. Yeah. So we conveniently skip that step, but that's the main part. So what I'm saying is that that's the main content of the theorem. The rest is sort of like easy applications of these calculus rules. So if this is good, then let's try to show. Okay, by the way, there is a bit of like argument here as well. So this converges to Z, this converges, and then I have a little OP of 1 here. So there's a bit of Slutsky there as well. So this convergent distribution, and I have a sequence whose difference to this is OP of 1. So this has a convergent distribution. Right, so it's not a Slutsky, but we are basically using the part F here. So that delta n is converging to this in distribution, like V negative V theta inverse. So this is saying like V negative theta inverse delta theta naught. This is converging distribution to blah, blah, blah. And this is basically, you can take yn to be this. So take xn to be that, and then yn to be root n theta hat n minus theta naught. So we know that the difference of these two sequences is OP of 1, and so the second one has convergence distribution. So there's this piece there as well. Okay, so like once you get comfortable with this, you just automatically do it, but there is a bit of argument there as well. Okay, questions? So okay, so let's try the proof. So the proof uses this idea, which is very common in classical statistics, and that idea is to do Taylor expansion around whatever you care about. Okay, so in this case, we're going to do, so first we observe that theta at n is a maximizer of theta n, so mn, and because I assume that the theta naught is in the interior of the domain, and then theta at n is converging probably to theta naught, we can say eventually for sufficiently large n, we're going to be in, like theta at n is going to be in the interior of the parameter space with high probability. So there's no boundary issue. So when I try to maximize mn, theta at n has to satisfy the first order optimality condition. In general, it has to satisfy the first order optimality condition, but it would mean in this case that the derivative has to vanish. If your estimator or like optimization solution is at the boundary of a space, then the derivative need not vanish like in every direction. It's just direction along with the boundary, not orthogonal in the orthogonal direction, because you can't move away from the set. You can't have a component which is not there. So this is key. It allows us to assume that basically you're doing unconstrained optimization. So if you're within the interior, the derivative, like in basically in every direction, has to vanish at theta at n, and that's fine. So this follows from this and the consistency. Now we Taylor expand around the theta naught. So m dot n. So we have this equal to 0. I'm going to expand this function. So by assumptions that we made, so we're going to assume that this expansion basically holds. So m is like differentiable implicitly. These are assumed. So sorry, mn theta hat n minus mn theta naught, the dot with the dots, is going to be m double dot n evaluated at some point in between, and then theta hat n minus theta dot. Okay, and this is like a first order Taylor expansion with kind of maybe even not first order Taylor expansion, sort of like a fundamental theorem calculus, basically. But it's this form of Taylor expansion nonetheless. And then because this is a matrix, I've written it like that. But generally speaking, it's like you have a function, right? X is equal to fx naught plus the derivative at some point in between times x minus x naught. And if you want to expand more, you can say f prime at x naught, but then the second order. So this is like sometimes called Lagrange form of the remainder. Okay, so this point in the middle is going to be in the line segment. So this is the notation for the line segment that I'm using. The line segment between theta hat n and theta naught, and sort of it's an application of fundamental theorem of calculus plus mean value theorem if you want. It's like the basic Taylor expansion. So this is a random quantity because it depends on this, and not on theta hat and m theta, but it's like dependent because of dependent on theta hat and dot, and both of them are random. So this is very random, okay, a very random quantity, and by consistency, this is also going to converge to theta naught because it's in between theta hat and theta naught. It's not hard for yourself to justify that this is basically also consistent. It's consistent for theta naught, so you get theta and tilde is theta naught plus little OP1. Okay, that's good. Then this second step follows, which is the fourth step. So why this is true. So that's the stochastic equicontinuity. Okay, so you're assuming that m double dot n is stochastically equicontinuous. We're evaluating the point, which is random, but that point is converging to theta naught. So I can just replace this with theta naught and then pay a price, which is a little OP1. So that's the meat of the argument, which we sort of circumvent by that assumption. The next thing to note is that this m double dot and theta naught. So we basically reduce the problem to this. So I can basically sort of replace this, we'll see, with this guy. So this is itself an average. If you recall what this was, mn theta is just 1 over n summation I from 1 to n m theta xi. So then I take the double dot, which is the second derivative. This is a linear sort of constructed from these m theta xi's by linear operation. So the differentiation goes inside, so I get this expression. So because it's an average, we know a lot about these averages. In particular, we know that, and then it's computed at a fixed theta naught. Okay, so the only randomness is in the xi. So each term is IID. So what we have is this guy is going to converge in probability to its mean, right? So this converges in probability to the expectation of m double dot theta naught of x1. And this is by definition v theta naught. Okay, I can say that this guy is v theta naught plus a little OP of 1. Okay, so that's the statement. So this holds by the Weak law of large numbers. Okay, so far so good. Yes.
Sorry, maybe this is better as a question at the end.
Okay, just don't forget, we'll come back. So now I have that. So I now want to combine 4 and 6. Okay, combining 4 and 6, we get 7. So basically, I'm going to replace this here with v theta naught plus OP of 1. And I get 2 OP of 1s added up, I get low OP of 1. So this is like a continuous mapping theorem or a Slutsky, whatever you want to call it. Maybe a Slutsky better, call it a Slutsky. But that's sort of basically should be 5, it should be 4. Basically 4 combined, 4 and 7. Sorry, 4 and 6. This is like a bit messed up. 4 and 6 together, they give you that. Okay. Just plug this in for this, and you get that v theta naught plus OP of 1 plus OP of 1. We know that OP of 1 plus OP of 1 is little OP of 1. So you can see this calculus helps you like avoid writing a lot of unnecessary symbols. I could have called this something and then this something, and then you have to carry these, but you don't have to. So this, if you follow the rules, you end up with that statement. This is really good because this very horrible thing, W random quantity, you're saying that this is something constant plus something which is the zero probably. Next, you apply continuous mapping theorem with this matrix inverse function. F of x is x inverse, and because you assume that this is invertible, right? If you remember, this was the assumption that this is strictly negative definite. So implicit in this is that it's invertible. So there's no zero eigenvalues. Because it's invertible non-singular, this map, which is a matrix inversion, at a matrix which is non-singular at this guy is going to be continuous. Okay, so we can treat it as a continuous mapping. And it's going to be continuous in a neighborhood as well. So once you can restrict yourself, everything is like converging to theta naught. You restrict yourself to a neighborhood, it's continuous in the neighborhood, and then you apply it to this guy. And what the continuous mapping theorem is saying, so this is just rewriting this other side. So this is really the continuous mapping theorem. Okay, so something which is weighted plus OP1, I can pull out OP1, put the negative here. So this is basically saying I'm applying the F the OP1. Okay, so if you get comfortable with this notation, you can see this is really continuous mapping theorem applied with this function. Okay. So every step is sort of justified, but intuitively, so if this is converging to V theta naught, if I invert it, the inverse should converge to the inverse of this. Plus a little OP1. But formally, that's an application of the continuous mapping theorem. Okay. Sounds good. So let me pause here. Let's see, like, can you guess what the next step is? What will be the next step? So we started with this, right? I care about this part. I sort of, we'll see, this is also an average. So we know, but actually this we know that's zero, right, from here. This is an average, so I know a lot about that. I care about this part, and I sort of managed to show that this converges to something, and its inverse is also converging to something. So what should we be doing? Right. Yeah, so we multiply both sides by the inverse. That's exactly what we do. And so one side would be this, the other side would be the inverse of this multiplied by basically the negative of that. Okay, so that's exactly what I have here. If you just look at it, stare at it a little bit, this is just this, multiply both sides by m double dot n inverse. And then the first term is 0, so this is 0 again because of the first order optimality condition. And I'm just replacing this inverse with what I obtained in step 8. And so I get this result. Okay. At this point, I mean, this is the distributive part that Brian was mentioning. So I can distribute things, but this little OP of 1 multiplied by this is not going to necessarily work out for us. Actually, it's going to work out. It's fine. But what I'm going to do is like multiply both sides by root n, because that's the scale I care about. If I multiply by root n, I get root n here. I move the root n inside. So this part is sort of, let's see if I have it correctly. Yes, okay, so I can distribute, this is fine. So V theta naught, this is so far okay. M dot n theta plus OP of 1, M n dot. This doesn't change much here. Negative if you want. Doesn't matter, so negative can be absorbed. But then I multiply both sides by root n. So if I multiply by root n, I put the root n here and here. So you get this, this term is going to be that, and this term is going to be that. Okay, so multiply both sides by root n. Now we're going to use the property that this quantity is big OP of 1. Okay, this is big OP of 1. And then I have a little OP of 1, so the product would be little OP of 1. So why that this guy is big OP of 1? So M double dot
distribution goes to 0.
Great, yeah. So this is really another average. Right. This is an average. So this converges to, what does it converge to in probability?
The first derivative.
Yeah, at theta naught, let's say. Which is by assumption equal to 0. That's like the score function idea. So this is 0. Yeah, this is not very visible. So let's change the color maybe. Okay. And then I can have a CLT. So then root n times this guy is going to converge to minus the 0, right? Which is the mean converges to normal, mean, 0, and what will be the covariance matrix? We have covariance matrix of that, which we call as theta naught. Okay. So because root n times this is so from this we also get that root n m dot theta naught is big OP of 1. The reason being that convergence distribution is stronger than being uniformly tight. Okay, so this really is big OP of 1. And in times the OP of 1, the product is going to be so this is the part. So this is CLT, this is from uniform tightness. Sorry, convergence distribution implies uniform tightness. Convex distribution. The product is little OP of 1, and so I can replace this with little OP of 1, and so this part we actually already showed. To be honest, this was really, if you look at this, this thing is really root n m dot theta naught is really this guy. M and theta naught is really this quantity. Okay, exactly the way that we defined it. This really is nothing but delta and theta naught. So I get the result. So the just proving that this is little OP1 is the end. So we have the expansion that we wanted. So the rest we did actually. Okay, the proof is done. So it's like a very nice collection of application of these results. And the only thing that we sort of avoided is this. The hard was like the step 4, which is like we use this high-powered definition to basically get around that, and then someone else has to prove that later for us. But the rest sort of follows once we make that assumption. Yes.
Two things,
Yeah.
One is, why is it that the point you get about well, versus can you do mean value theorem in a possibly n-dimensional set, right? Like the parameter space could not be.
Yes, you could.
Right?
You could.
It's like a neighborhood. Mean value thing?
No, because the only you care about the line segment. Basically, you can define. Let's say this is a good exercise for you that you can. I can define a function. Let's say. Let's say is m dot, and let's say it's like a theta hat. Say plus. Yeah, let's do this. So you can see this, define it in 0 to 1. Right, at 0, it's going to be theta naught. at 1 is going to be theta hat n, and it's univariate, and so you can do the expansion, and then there's something like this follows. Okay. Yeah, so you don't need to worry. And then a lot of the things you actually did it in your homework problems as well. Convexity, things like this in multivariate case reduced by this trick to univariate case. Yes, yeah. Because you care about just these 2 points, and this is why like this is going to be the line segment. So it's going to be like somewhere in this thing. 0 t for some t 0 to 1, you have the expansion, and that means that that's going to be the line. So you can write this as like a convex combination, basically. It's equivalent to 1 minus t times theta naught plus t times theta hat n. Okay. Yeah. So what was it?
Was for continuity, I think theta tilde. Right, you have to say that for folds, right? But I feel like we know that theta hat or mn theta hat is exactly to this. Does that mean that also like the thing between them gets squeezed into being also like
that's exactly what the condition. So if you remember this, that's the thing that I'm using. So the only reason why this like introduces stochastic continuity is that this interesting property holds. So if you have a sequence of functions, so these are, let's say, m and theta. So these are our functions. They're stochastically continuous at theta naught, and I have a sequence that converges. In our case, it would be like theta tilde n converges in probability to theta naught. M and double dot, let's say this is double dot, is equicontinuous, like it's stochastically equicontinuous at theta naught, then I can conclude that M double dot n theta tilde n converges in probability to, not in probability, but difference is converging in probability to 0, which means that I can write the statement that I made. So theta n is not continuous. It's like just a random variable, like a sequence, right? But the mn is equicontinuous, and evaluating that equicontinuous that sequence of equicontinuous stochastically equicontinuous sequence of functions. I'm evaluating it at this point. So
it's because it's property of the function, right? And not the domain. That's the function will be stacked. That's the continuous. So you can pick any sequence. And it'll still hold it.
This holds for any convergent sequence in probability. Yeah. Yes. It's like the strength of that condition, basically.
And then the assumptions are as well. The assumption in the group was that for each mi, right, like in the sequence, all of those double the second derivatives are stochastic.
So stochastic continuity is like properties is like a collection of functions or sequence of functions. So this whole collection as collection is stochastic equivalent. Okay. We can read Pollard's book and like empirical process theory books, try to like see how to show it, but it's similar to the kind of ideas of proving uniform laws of large numbers. A lot of technical tools go into trying to prove that, and so you can have like simpler conditions that can be verified, but I like this version because it's just exactly what you need sort of to get the result, and in each case you can try to verify that whether it's false or not. And here we're not going to worry about like explicit conditions. So sufficiently regular models, this is true. Sounds good. So I encourage you to go through the proof and then try to like justify each step for yourself, or just try to do it, like do the Taylor expansion and try to argue for yourself the final result to see like exactly what pieces we use. So I try to like have the justification of every step here, just in case you want to like make sure that you understand. So every little step we use something there. But once you like get comfortable with this sort of ideas, you can see it's like very easy to write down. It's like it's not like a straightforward proof. It's sort of straightforward if you use these little OP of ones. If you don't, then it's going to be a little horrible to write down. So that's the power of these little OPs, big OPs. Okay, I have a little condition here that Yeah, sort of if you have like uniform dominance, then this thing is going to be stochastic equicontinuous. I'll leave it to you to look at it. I also have a homework problem. I think this is like the third derivative. You can see triple derivatives. So if the triple derivative is bounded uniformly, then you have things going on, and that's how you sort of see triple derivatives come in when people try to prove like asymptotic normality of MLEs. If I remember, I'll post the homework problem for you to just not formal homework, but you can try to prove it. Like under these conditions, it's not hard to prove the stochastic continuity. Okay. So let's see what happens in the case of the MLE. So in the MLE case, that m theta is like log p theta of x, the log likelihood. The first derivative is the score function, as was mentioned before. S theta is the Fisher information, as we saw. V theta is negative Fisher information. So that quantity, which was, if you remember, the asymptotic variance or covariance matrix is V theta. I'm going to drop the theta naught. It's just theta is like the true parameter. So V theta inverse S theta, V theta inverse. So if you plug in these quantities, basically all of them are I theta or like negative I theta. So if you do it, you get triple I theta. So two of them cancel, like one remains, which is I theta inverse. So what you get is that the MLE is asymptotically normal under those conditions with the asymptotic variance, which is the inverse of the Fisher information. And if you recall the Kramer-Rao bound, the inverse of the Fisher information is sort of the lower bound on the. So think of this, the univariate case for simplicity, just 1 over I theta naught. That's the variance of the lower bound and the variance of any unbiased estimator. So people interpret this as MLE is asymptotically efficient. So asymptotically achieves the Kramer-Rao bound. Although Kramer-Rao bound itself is not an asymptotic result. So you can have estimators that do better than Kramer-Rao bound asymptotically at certain points. A great deal of classical statistics is trying to make the statements more rigorous. So then we claim that MLE is asymptotically efficient, or asymptotically, what does it mean to be asymptotically efficient? We're achieving Kramer-Rao bound. And that sort of led to a lot of like technical tools people trying to make this statement more clear. But at this level, it's just this is the asymptotic variance, however you want to like interpret it. But is there any questions? I might say a few more words that Kramer-Rao doesn't hold any limit. But yeah.
Sorry, real quick about the proof. Did we prove that the difference between beta hat and beta naught is like something plus OP1, or do we prove that it's actually V times delta?
No, the theta hat n is consistent. So this is part of the assumptions. So theta hat n this is saying theta hat n is theta naught plus the OP1. So this is one of the strong assumptions.
I just copied that. I see that the proof that the actual result is that it is V delta plus little OP1.
Oh, you're talking about which maybe I missed. Okay.
Yeah.
Okay. Good. But yeah, so the consistency is part of this. Just remember that you're not proving here that MLE is consistent. So usually, like you need separately prove consistency. Once you have consistency, a lot of things simplify because then you can reduce everything to a neighborhood of the true parameter, and close to the true parameter, like everything is sort of regular. Consistency is usually considerably more difficult to establish because it's sort of a global property. So for MS estimator. So once you have that, a lot of things sort of simplify asymptotically. Okay, so remember this is like a classical result that is worth remembering. So MLE sort of in regular families has this asymptotic normality result, like asymptotically efficient in the sense that asymptotic variance is 1 over the Fisher information. In the interest of time, I'm going to skip this. This is called Hodge's super efficient example. So this shows that you can like manipulate any estimator at a single point such that we can like violate the Kern-Raoult at that point. So you can have like an estimator that's like everywhere bigger than sort of like these are called asymptotic variances. So the asymptotic variance of it is always bigger than or equal to 1 over I theta, but at a single point has like a variance of 0, let's say. This is doable. It's not hard. And this the modification is here. So it's Hodge's sort of example. And so this led to a lot of like activity trying to like come up with an explanation of, okay, so this could not happen, for example. It could happen at a single point or like a finite number of points, but not a big number of points, for example, like trying to like argue like why a different kind of convergences, what it means to be like asymptotically efficient. So I'm going to skip this. Just remember that doesn't the Kern-Raoult bound doesn't necessarily hold uniformly in the limit. I'm going to talk about a bunch of other results. I wanted to like finish talking about asymptotic results today and maybe to start talking about hypothesis testing next time, but we'll see like we have a bunch more stuff to talk about. One is delta method, the other is asymptotic relative efficiency, and then asymptotic confidence interval. So let's try to get through this. Delta method is another powerful extension of the CLT, which again is proved by Taylor expansion. So the idea is that if I have a sequence of not necessarily estimated, just any statistics, and I have some sort of a limit theorem for the sequence, AN could be like root n, for example, often, but sufficiently general result holds for any sequence AN that goes to infinity. The limit z could be anything as well. Now I apply a function to this. It's like the setting of continuous mapping theorem, but here we're going to assume that the f is differentiable. And I say something about the limit of this. Okay, so if the function is differentiable, it's certainly continuous, so we know that it converges. Well, first, I should mention that the consequence of this is that xn converges to theta in probability. I'll mention that later. But then, okay, maybe mention it here. So if this is the case, we know that AN xn minus theta is big OP of 1. Okay, because it converges in distribution. Then I have xn is theta plus divide both sides by 1 over n. So it's OP of 1 over AN. So this notation exactly means something such that when I divide it by A over n is OP of 1. So exactly it's for something which is when I divide it, so it's going to be like basically OP of 1 divided by AN is just OP of 1 over AN. That if you understand like big O, this is the same meaning. So OP of 1 over N is like something that it just basically means this thing, something like that, and something like this is going to 0 because you can see like the 1 over AN is going to 0, and I'm multiplying it by OP of 1, so this has to be like little OP of 1 by the property that we mentioned. Okay, so this is really theta plus OP of 1. You don't have to like write it in this notation. Just write it like this. And it's just something like going to 0 times big OP of 1. I could say it's just like 1 over AN big OP of 1. So you can see that this condition, if you assume this, implicit in it is that xn is converging to theta in probability. Okay, so it's already consistent for theta. And then we know that fxn is converging to f theta by like continuous mapping theorem. The question is that can I get an asymptotic result for it? And this delta method is saying that yes, you can like easily translate this result into a result on f of xn, so f of xn minus f of theta at the same sort of the scaling is going to converge to Jacobian of the transform, which is a matrix times Z. Okay, so a linear transformation of basically Z. And the Jacobian is just this matrix. I'm here assuming that everything is multidimensional, but I guess like a univariate version of it is also true. We'll see an example of it. So, okay, so here's a simple, like for the case where everything is one-dimensional, this is just going to be the derivative. So a univariate function of phi to xn minus f of theta converges in the limit to, if I multiply by an to the derivative of f at theta times c. That's the ultimate. It's a very powerful method because we can just apply any nonlinear function, which is differentiable, and then get a limiting result. So let's see the proof first. If you have, so that's the argument that I mentioned. So if you have this, it's going to be big OP of 1, because this is going to 0 to infinity, this is going to be little OP of 1. So we have that by differentiability. So we have the first order Taylor expansion. This is this plus j theta times h, that's the derivative. The derivative is really a linear map whose like matrix is j theta. And then I have some remainder term, which I write like this. The property of this remainder is that if I divide this, so if whatever this is, let's call this, let's say, I don't know what should I call it, mh, whatever this is like mh divided by, this is going to 0. So that's how I wrote it. So this division I like, or this ratio I'm calling RH. So now the way that I wrote it, RH has to go to 0. So that's the meaning of differentiability. The RH is O of 1 in the classical case. And I'm going to define, at 0, it's not defined because it's like that. So at 0, I'm going to define it to be 0. So it's going to be continuous at 0 because it's converging to 0 and defined to be 0. So it's continuous at 0. Then I'm going to apply this to, so take h now here to be x minus theta. And if you plug in, just plug in the above, you get the statement and multiply everything by, so move this to the other side, multiply by an, and then you move the an inside here. So multiply each one of these. So an goes in, this is a norm. So I get these. Now this converges to z by assumption, and then j theta times that is going to converge to j theta of z by the continuous mapping theorem. Okay, so that's the continuous mapping theorem, or Slutsky if you want. And this one, this thing is OP of 1. So the norm is going to be bounded in probability. And by continuous mapping, so this is OP of 1. And so the first that R is continuous at 0. So this is going to be a little OP of 1 as well by continuous mapping theorem. Okay. And so little OP of 1 times the big OP of 1 is going to be OP of 1. And then we're done. Okay. So not very like much simpler than the MOE analysis. It's just that we do the Taylor expansion to the second order, if you're the first order, but the remainder is the second order. Okay, so go through the proof. It's not really that difficult. It just this version is from the kind of proof is from the asymptotic statistics by van der Waart, and the advantage is that you're not assuming that the function is continuously differentiable. It's just enough to assume that it's differentiable, because differentiability just means that this converges to 0. I can modify it at 0 to be continuous, then I can use the continuous mapping theorem. We don't need the function to be continuously differentiable, just differentiable at the parameter theta. Okay, so an application of this is application. Here's an application. So we have xi's are IID, mean, mu, variance, sigma squared. By CLT, we have that root nx bar n minus mu is normal 0 theta. So suppose I'm applying e squared to x bar. So we know that by continuous mapping theorem, xn squared has to converge in probability to mu squared. So we want the deviation. We want to study the deviation. Delta method says that if I look at this is going to be converging to the derivative of this map at mu times the limit of the other one. So the derivative of this the mu is going to be 2 mu, right? And 2 mu times the standard normal is going to be another normal, which means 0 and variance multiplied by the square of this factor, which is like 4 mu squared. So that's a very nice result. It shows you that this holds. An interesting case happens when mu is 0. Okay, when mu is 0, the result still holds, but you get a normal 0, 0. Okay, normal 0, 0 is really 0. So we proved that in that case, root n, and this is going to be also 0. So root n x bar n squared is converging this distribution to 0. And that's fine. But what it suggests is that the root n is not the right scaling. So it's converging faster than root n. So you have to scale it by something bigger to get something stable. And in this case, we know what happens because I have to multiply by n goes inside. So I get, so this would be, I know that n times x bar n squared, in that case, when mu is 0, this is going to be root n x bar n squared. And I know that this converges by continuous mapping theorem to z squared, actually, because this is converging to z. So by continuous mapping to z squared, so this is going to be chi squared. So in this case, the right sort of asymptotic limit is first I have to multiply with something bigger, which is n, and the asymptotic limit is chi squared. So the delta method is still fine, but this version doesn't work. What really you can do in these cases is if you want to apply the delta method, this suggests that the first order theta expansion is not going to work because this is going to vanish. Okay, so you do the second order theta expansion. So you can upgrade the delta method. So really the second derivative is going to come, and you can prove this result by a delta method, which is, we have it here. Yeah, some sort of result like this. So if you have, as a k is equal to d equal to 1, this converges to a normal, it means 0 and minus sigma squared. The derivative is 0. Then you do the second order theta expansion and you prove something like that. So n times fxn minus f theta converges in distribution to, you get this chi squared category. This informal definition, like derivation is something like this. You can just figure it out for yourself. And we're almost done. There's another example with the Bernoulli that you can do. Yeah, and then maybe let me just mention this and next time talk about asymptotic relative efficiency. So you can do everything in the multivariate case. So that's the multivariate version. So the delta method that I mentioned is the multivariate version. So let's say I want to prove something about the sample variance. So you write down a multivariate CLT. So we have this multivariate average, and this converges to a multivariate normal. So you can figure out what the mean would be this, because this first and second moment in the covariance matrix, which you can calculate. So this depends on the fourth moment of your distribution under consideration. And then once you have this, then sample mean is this, sample variance is obtained by this. So if you apply, so you can actually figure out the joint distribution of the sample mean and the sample variance. So if you apply this this goes from R2 to R2. If I apply this, I get from this guy, the joint distribution of x bar and Sn squared. And then this converges to the Jacobian times this. And so I give Jacobian, sigma Jacobian, and then you can figure out the sort of details for yourself. This gives you like a joint understanding of the distribution of sample mean and sample variance at okay, thank you guys. Next time I'm going to come and finish these two more things, asymptotic relative efficiency and confidence intervals, and then we move on to hypothesis. Thanks.